everyone. Today we start our Data Phoenix webinar. With us, Glenn Jocher, founder and CEO of Ultralytics. Today we will speak about YOLO. We'll see the demo, and you can ask questions using Slando. We share the link on our YouTube. And also you can join us on Zoom and we can have the discussion live. So welcome to speak with us on the Zoom as well. Don't forget to subscribe to our YouTube channel to see our next webinars and see our all videos which we do. So don't forget to subscribe. Now I give the microphone to Glenn.
All right. Well, thanks, Dimitri, and hello, everybody. It's nice to be here on this Data Phoenix webinar. So I'm Glenn Jocher. I am the founder at Ultralytics, and I think probably better well known as the author and maintainer over at YOLOv8, which is a really popular open source vision AI. So I've got a few slides here where we're going to talk about Ultralytics, the background, how we got started, how we got into AI, and our latest adventures in the AI space. All right. So Dimitri, I'll just go ahead and share my screen here and start this up.
Yeah.
All right. Let's see. Okay. Here we go. Okay. Can everybody see these slides? Can you see this, Dimitri? Looks like yes. Dimitri, you see my slides?
Yes, yes.
Okay, all right, perfect. I never know. Okay, so I think I'd like to start the slides with a question about why, right? Why do we do things? And this is always the ultimate question, really. I started off doing a lot of physics, particle physics, and in a lot of these fields, we always search for the how do things work? Like how does one thing convert to another thing? How does energy turn into matter? Things like that. But once you answer enough of those questions, you start wondering something a little deeper, which is like, why is this happening? Why are we here? What are we doing? And like, what is our purpose? And I think I've found my purpose recently in these last few years in the AI space, where we've had a tremendous impact helping a lot of people and a lot of causes around the world with simple, effective, and free AI solutions in the form of YOLO models that have been deployed in a lot of different places, doing a lot of good. So let's see here. Let me start from the beginning because it looks like I'm on the last slide. Okay, so this is me. I'm Glenn, and I started Ultralytics a while ago now. It's been 9 years. We just had our 9th birthday. It's April 1st, 2014, when I started the company, and it was just me at the very beginning. And I initially started doing particle physics applications as part of Ultralytics. Ultralytics got our first contract from some intelligence agencies in the United States. We worked with a couple different agencies on particle physics programs. And this was really interesting. I had a big passion for this back in the day. The particle physics that we were tackling was mostly in the domain of antineutrinos. And this is doubly exciting because antineutrinos are a real mystery. We don't really understand them. And we were hoping to develop innovative technologies to detect antineutrinos, accumulate statistics on them, gain a better understanding of how they work, and in doing so, build products that might be able to exploit those behaviors of the neutrinos. The most famous and most interesting aspect of these particles is that they oscillate between different flavors. So they don't just exist in one state. They have sort of 3 different flavors or personalities. And depending on when you look at one and how you look at it, you'll see one facet of it. It's a big mystery. And this is also how I got into AI. We started doing data analysis in these particle physics experiments because the traditional techniques that we were using weren't producing the results that we were hoping for. We had promised the funding agency, that the technology would be mature in a pretty short timeline, just a few years. But it turns out that when we actually built these detectors and deployed them and started collecting data, the data was much messier than we had anticipated. And we had problems filtering out the particles from their background. And so this is a traditional classification problem. And I started tackling it with traditional techniques like parameter estimation, Bayesian techniques, and I couldn't get the results I wanted. And so I went out into the literature and I started looking at other solutions for estimation, for parameter estimation, for state estimation. And this was back 2015, 2016. And AI was just starting to get tantalizingly interesting in the vision space. And like one of the first things that I saw was that I started uploading my photos to Google Photos. And one day I realized that I could search Google Photos. Like I could search for a dog and it would pull up pictures of dogs. And I thought, oh, this is strange. Like, how is this working? Like, how is this possible? And I started digging a little deeper and I realized that Google was applying classification models to the pictures and then indexing them, adding metadata and allowing them to be searchable like this. And I started doing a little more research into the field and I saw that it was immensely popular, especially compared to the particle physics work that we were doing. So in the work that we did, it's very specialized. And when we would publish a paper, we might get maybe 10 citations after a year or two. And that was a success. But when I looked over at the vision AI space, you know, a company could publish a paper and get thousands of citations in a couple of years. So it was orders of magnitude more popular and there were more people interested in it. And it seemed to be having more of an impact on the day-to-day lives of people around the world. And this is important to me because I was always a bit frustrated in the particle physics experiments that we ran because they seemed to be more distant and more abstract in the benefits that they provided. So we learned more about the universe, but sometimes that knowledge, if it's not translated into something that affects your life or your day-to-day behavior, it's a bit unsatisfying. So I wanted something more concrete, something that I could point to and say, oh, we're making the world a better place. Like people are better off because of this. And so this is how I started getting more and more interested in the AI space. And right around the same time, something else really interesting happened. So this is when the first YOLO models were being released and shortly after that abandoned by their original author. And so even though I'm most famous for YOLOv8, I did not author the original YOLO models. These were created by a guy called Joseph Redman. He was doing his PhD thesis and he had an academic advisor called Ali Farhadi. And they paired together to do research in vision AI. And what they saw was that the existing architectures of the day were mostly based on faster RCNN, fast RCNN. And these were two-stage models, which means that they would pass through an image once, they would identify regions of interest, and then they would take a closer look at those. And Joseph's main contribution to the field was merging these two into a single pass. And this is the fundamental advantage of a YOLO model versus a more traditional architecture like RCNN. It's that it only passes through image once. And because of that, it's fundamentally faster. There's less operations, it does everything at the same time. So it's doing more multitasking. And for that reason, it originally got slightly worse accuracy, but much faster speeds. And so this is right when I started getting into open source also. So a lot of things started happening around the same time for me about 3 or 4 years ago. So the particle physics efforts wound down. We did not meet our goals. The funding agency cut our funding and everybody was CAS free. And so Ultralytics had all our eggs in this basket. So this is a big crisis for us. We lost all our funding and this gave me a lot of time to reflect, but also to sort of pursue my interest that I developed in AI. And my initial work was to start copying the YOLO repositories that had been built up by Joseph Redman and port those over into Python. So Joseph, while he created these amazing models, he created them in C in a framework called Darknet that he created himself, which is very impressive. But for other researchers, hard to work with, not as well documented and maintained as some of the emergent frameworks of the day, the two of most popular, which are TensorFlow and PyTorch. So I took a look at my options for TensorFlow and PyTorch. And being more familiar with Python, I went with PyTorch because it was easier to work with. And it threw errors exactly where they occurred. I didn't have to compile a static graph, which was not a concept I really liked. And I think I made the right choice. Now, PyTorch is much more popular in the research community. So once I picked my framework, I started working on copying Joseph's AI architecture. And the first step was copying the prediction step, the inference in the architecture. And that was actually not that difficult. It took me a few months and I was able to reproduce the same results as the darknet models. So I had a PyTorch version of YOLOv8. And you can see this now. It's all this history is written in stone. Since it's on GitHub, it's all open source. And the next step was to try and replicate the training. And this was much more difficult. This took me the better part of a year. And it was much more difficult because there's so many more parts that can go wrong. There's loss functions, there's augmentations, and the entire combination of those together means that there's a lot of different things that could not be quite right. And sort of like launching a rocket, if one thing is not quite right, then the whole thing can go wrong. So after I replicated the training and the inference, I had finally a Python version of YOLOv8. And at that point, I didn't know what to do. So I just kept working on improving it. And eventually, a few months later, I managed to surpass the original YOLOv8 accuracies, which kind of surprised me. But I was nowhere near SOTA. By that point in time, new architectures had come out, new companies were launching things. And this hobby of mine had grown kind of popular. Since it was open source, people had noticed it and they started pitching in and contributing, which is really awesome. It's one of the facets of open source that I was a little scared of at first because I'd never done open source work. And from the outside, I thought, oh, people are just going to take my work and run off with it, which is true. But there's other people that take a look at the work and help improve it, which is amazing. And it's not something I saw before when I was working on programs for the government, which didn't want me to open source anything. So me and my team of contributors were steadily improving YOLO. And this brings us to about 2020. So this is the second bar here. And we'd improved YOLOv8 so much that it was significantly outperforming the original. And I realized I had a bit of a problem in communicating this to people because I'd tell people in meetings and open source gatherings about my efforts in YOLOv8 and how the performance is really good. And they'd say, wait, Glenn, no, something's wrong here. I think you did something wrong because that loss function is not in the paper. Or like this augmentation shouldn't be here because Joseph didn't do that. Oh, and I forgot to mention, so Joseph and Ollie had, they'd left their YOLO efforts behind them at this point. They'd split ways for different reasons. So Ollie went on to found a startup called Xnor.ai, which he sold to Apple for a significant amount of money. And Joseph had started doing talks for YOLO, kind of like what I'm doing here. He got invited to a big TED Talk. And there's a huge audience, and afterwards, everybody gave a big applause. And some military officials came up and expressed their interest in utilizing the technology in some military programs. And Joseph did not want to be a part of that. And he realized that if he contributed more on the open source side, then the technology could be adopted for these use cases that he didn't want it to be used for. And so he thought that the best way to prevent that was to stop work on it. And so that's what he did. So he set it aside and he's now in teaching. So he's teaching AI now, but he's no longer working on YOLO models. And this left the YOLO ship drifting without a captain. And so the work that he'd started was picked up by a contributor in Moscow in Russia by the name of Alexei AB. And Alexei diligently worked on maintaining the darknet repository, the fork that he had, and improving it. And him and I communicated a lot in those days, and we bounced back ideas for how to improve YOLO, how to make it faster and more accurate. And Alexei was also working on improvements of his own. And so at this point, when I'd realized that I needed to, I think, launch a new architecture, call it something different so that people realized that this wasn't YOLOv8 anymore. It had changed enough that it was now something different. The performance gap was enough that people would recognize it as a new product. And so I got about creating a new repository, but I started this new one in private to give me a chance to clean it up first before I open sourced it. And so I worked on this new repo for a few months. and I decided it needed a name. I wasn't sure what to call it. So I decided just to call it YOLOv8. I thought, okay, this makes sense. And right when I was about to launch it, one day I get this notice from a colleague, and he says, Glenn, have you seen this paper that came out by Alexi? And what had happened was Alexi had been doing the same thing. He had been working in private on his own architecture, and he launched it with a paper in, I think, March of 2020. And so he beat me to it. It caught me off guard, and I was very surprised. And I thought, wow, okay, now thought I had a bit of a crisis moment, but I calmed myself down. I sat down, I read the paper, and I realized that what I'd been working on, I believed still to be better than what had come out here in this YOLOv8 repo. But the YOLOv8 repo did present improvements. And so I had the advantage of hindsight. So I sat down and I worked on integrating what the improvements that YOLOv8 provided into mine. That took me a few more months. And then in late May, I was all ready to go. But again, I had a naming problem. And so I sat down, I said, okay, what do I call this again? And I thought, well, the easiest thing to do is just call it YOLOv8. So I changed the name from YOLOv8 to YOLOv8. I open sourced it, and there was a tremendous amount of controversy. So there's a lot of criticism from a lot of people, both towards Alexi and myself, for not being directly attached in an academic sense to the original authors. So I put some disclaimers, and I took some of the criticism, but ultimately I just got back to work. So I think anytime you're doing something, something significant, there's going to be criticism. And I think part of your job is to take the slings and arrows of your critics and just continue moving forward. And so I decided to just keep working and doing what I was good at, which was improving YOLO. And so I kept focusing on this. And the YOLOv8 that we originally launched advanced and changed and evolved. And every few months, I'd release a new release. So the new releases would have architecture improvements or introduce new features like export to new formats and so on. So this took me through the better part of 2021 and 2022. And last year, we had some new releases in the YOLO space. So the YOLOv8 in this time period got really, really popular, like much more popular than I ever anticipated. So when I initially started working on YOLO, I thought I'd create just an internal product or an open source product that wouldn't really attract much attention. But the intention was really for us to use it in sort of like an end-to-end pipeline to create an app that we could use for a product. And we realized that every time we tried to create a product, like a smart cities app or a medical app or sports app, we'd run into issues because we weren't domain experts. So for example, if I'm creating a smart cities app, it helps to know, say, the politicians or the administrators or something like that, so that you can place cameras, interact with them. If you're a sports app, it kind of helps to have some knowledge of, say, like a soccer league, or be able to talk to like a governing council there. Or if you're a health app, it helps to have some medical experience, be a doctor and so on. And so we weren't any of these. And so while we had a good knowledge of the technology, we lacked domain expertise and more necessarily connections within that domain inside the business community. And so we had trouble launching our own end products. And so we just kept working on YOLO, which we seem to be pretty good at. And that takes us through last year. So for 2021, I focused mostly on improving YOLO, improving the accuracy and the speed. And once I'd gotten that to a good point, I sort of set that R&D aside, and I focused on adding features. And the features were things like exports to almost every format and benchmarks, which are really important. So once you export, you want to make sure that the model doesn't lose accuracy. You want to compare speeds in different export formats and different platforms, things like this. And so by the end of 2022, YOLOv8 was pretty performant and it was pretty feature rich. But since we'd focused most of 2022 on adding features rather than improving R&D, a few competitors popped up. And since YOLO gotten so popular, some of these competitors were really big. So a big company in China came out with something called YOLOv8. The company's called Meituan. They make delivery robots, and they've been using Vision AI in their products, and these little delivery robots that go down the sidewalk. And they wanted to create an open source tool. I think most of the benefit there would be from open source contributions to help them improve. So that was a big surprise. And then a few months after that, our friend Alexi showed up again. He paired with another prominent researcher who I believe is in South Korea and goes by a GitHub handle of Wong Kin Yu, and who's also contributed significantly to the YOLO architectures, most importantly through CSP bottlenecks. So they paired together to launch what they called YOLOv8. And so again, all this drama came back from 2020 with different versions of YOLO launching in quick succession. And we realized that we'd sort of taken our foot off the gas pedal here and allowed a gap to open up that some other companies jumped into Alexi. And so we got back to work. So by this point, Ultralytics was a lot bigger than when I started. So in 2020, when I started working on YOLOv8, I was just by myself. It was just me and a laptop and a phone connection. And I would just kind of do this in my spare time. And by the time, at the end of 2022, we'd grown to about 10 people, multiple ML researchers in the US and China and India, and a bigger team too. We had a marketing team to let people know what we're up to. And also we started creating a web product because we realized that no matter how simple we make YOLO, which is one of our main priorities, it's still going to be kind of complicated because it's essentially a code base. So you need an environment, you need to know code, and not everybody knows that. So we wanted something that mobile developers and web developers could also get into. And so for that, we started working on Hub, and that's where we get to our third bar here, Ultralytics Hub. Hub and YOLO now are the two pillars of Ultralytics. YOLO is our open source AI, of course, and Hub is an online way to train and deploy it. Super simple and also free. So we got back to work and we scraped together all the literature we could find, all the recent R&D and the papers that had come out. We talked to ML engineers at the other companies like Meituan, and we also set up a big event called YOLO Vision. We realized there's so much activity in YOLO that we wanted to get everybody together, get all the smart minds together, hear all the opinions. And so we created this virtual event last year. We'd never done this before. We called it YOLO Vision. And it was such a success. We got like 20 or 30 companies, lots of presentations and lots of participants. And now we're going to have it again every year. So after this event, we started in earnest work on YOLOv8. And this began in about September of last year. So we worked in private for about 3 months. We tested out different advancements from different sources, mostly from YOLO community models. So we went to, for example, Baidu. We looked at RTM models. We also looked at Paddle. We looked at MedV with their YOLOX models. Of course, we looked at Meituan also with YOLOv8, which we found very impressive. And then, of course, Alexi's paper and Wong Kin Yu's paper, the YOLOv8 paper. We looked at this, we looked at the models. And typically when we compare architectures, it's hard to do that directly in a paper. Sometimes papers are a mix of sort of fact and marketing, and it's hard to separate one from the other. So usually what I would do when I looked at an architecture is I would glance at the paper, look at the repository, and then I would typically export the model to Onyx, which allows for a simple side-by-side comparison. And I'd use a viewer called Neutron Viewer. So once in Onyx format, then I would just go through layer by layer and try and identify changes from what we had. And there's kind of a recurring theme in the YOLO community these days. Since YOLOv8 is so dominant, so popular, a lot of the models were based on YOLOv8, maybe the code base, or maybe simply the architecture, or both. And they would have slight changes here and there. And so it wasn't as difficult as it sounds. Like when I say this, it sort of sounds like I'm looking at the green matrix screen with the code going down. But after kind of looking through enough models in Neutron, you start to notice trends like the C2 blocks or the C3 blocks. You sort of see a silu, and you can kind of start to like read the model. And so this way I could just eyeball changes. When I had identified a change, I would kind of queue it up for our experiment. We'd run an experiment with it. We'd see if it improved the results. And the important thing is we'd isolate changes. So if a competing architecture had, say, 3 changes, we take one and we just apply that single change to a YOLOv8 model, and we compare it against a baseline. So every time you do this, it's important to be able to assign responsibility for an effect to a cause. And by just changing one thing at a time, this is how you do this. So we accumulated a lot of different changes, and we implemented them all into the YOLOv8 models, and then we started training them. And the training took a long time since we're now supporting many more tasks. So when I first got into YOLO, when I launched YOLOv8, I created 4 models. And this was inspired by efficient det by Google, which was inspired by efficient net, also by Google. So efficient det, one of their main contributions was called compound scaling. So they found that if you scale a model in width or in height, it improves. But if you scale it by both at the same time, then you get a bit better improvement, which is maybe more than the sum of its parts. And so I took a look at YOLO and I thought, well, YOLO also needs this. This is a very big benefit because it allows users to select a model from a wide range, from very small and fast to very big and accurate. And so I applied compound scaling to YOLOv8, and I just launched with 4 different models. And so it took me a while. I convinced the big cloud providers to give Ultralytics cloud credits. So I went to Google and I went to Amazon and I got accepted into the AWS Activate program and the GCP Cloud Credit program. So if you have a startup or you're doing research, I definitely recommend trying to get into those. That gave us the hardware access that allowed us to train YOLOv8. But 4 models wasn't too bad. But by the time we'd gotten over to our YOLOv8 models, the YOLOv8 detection family had grown to 10 models. We added a nano model to the family, and we also added P6 models. So we had 5 P5 models, and now we had 5 P6 models. And if you don't know what that means, a P5 model simply means that the input image has been divided 5 times in a row. So when the image comes in, let's say it's size 640, then as it progresses through the model, it will become narrower in width and height, but elongated in the channel dimension. So if it starts out as 640 by 640 with 3 channels, RGB, it might end up as something that's like 20 by 20 by 1000. So as it goes down, it's going to be progressively downsampled. And if you do that 5 times, it's called a P5 model. If you do it 6 times, you end up with something that's even smaller in width and height. That's a P6 model with stride 64. So these P6 models are trained at 1280, which means that they take 4 times longer. So by the time we got to V8, we had 5 times the training requirements. 1 for the P5 models and then 4x for the P6 models. And not only that, but we'd also added tasks. We started doing classification and also segmentation. And so we had a lot of training to do. So we started the training about a month early. We wanted to launch in December, and we didn't make that. So we pushed that back to January. But the training for the January 10th launch really started kind of like around December 10th. And at that point, we froze the architecture, and that was a really big deal. We had to set in stone a certain date past which the architecture would no longer change. So even if we found new advances after December 10th, we wouldn't implement that because we'd have to restart the training again. And given our limited resources, we just have 1 server that we do all our training on. It would have taken pretty long. So we did all this training and we got it done just in time. We launched January 10th, and that was just been about 2 months ago. So now we've gone through this slide and we're almost up to the present day. So it's been a big whirlwind. We didn't have YOLOv8 as mature as we would have liked at launch, but I think that's always going to be the case. The important thing is to get it out, get it in front of the community, get people breaking it, let us know about it, and then iterate changes and improvements. So I think one of the main contributors to our success over the last few years has just been rapid iteration. Musk says that the limiting factor for any advancement is the rate of change that you can iterate. And that's definitely true. So we update YOLOv8, YOLOv8 on a daily basis. Even very small changes will push a commit forward to a PR. So if we see like a typo in a comment, even these sorts of things. So if you imagine a small improvement, not even in AI, just in anything that you apply yourself to, if you improve slightly day after day, you imagine where that'll take you after several years or even a decade or more. You'll have an amazing product that's just been iterated thousands of times. And it's so refined that you're going to have something completely different than what you started with. And that's where we are now. So the journey, of course, is still continuing. We're only halfway there, but we made big strides since we started just a few years ago. So we're looking at a few different use cases here for YOLO. We've got a sports app company that's using it to help kids train. It's kind of like watching their game, and it's giving them pointers. And it's got a really famous Premier League backer, Kevin De Bruyne. I think he's in Manchester City. He's financing this app, and it's using YOLOv8 right there at its core. And there's also research groups around the world using it for really interesting things. We've got a lot of undersea cases. It's kind of interesting. People are using it in submersibles on the sea floor at different depths and on the surface. Some of them are simply for tracking wildlife, like what you see here. Some of them are actually for tracking contamination and trash. And there's some plans in place even to help collect trash from the ocean using AI models that can detect it and scoop it out with robotic arms. It's really interesting. And on the right side here, we see an example for fire detection. So ironically enough, smoke detection actually works much better than fire detection. It gives you more lead time and allows you to see it from further away. But all these cases that we're seeing are examples of how we are improving problems in the world, in society. So for example, on the left side, a soccer app seems trivial, but at the same time, it's providing benefit to people who might not otherwise get this expert advice from players like Kevin De Bruyne. It's helping kind of spread more equality, more access to expertise. For water issues, it's having a tremendous impact. It's helping us clean up the ocean, monitor wildlife, and especially endangered wildlife. There's a organization called the Kashmir Wildlife Foundation, and they're using YOLOv8 in cameras around the world to monitor endangered species, snow leopards in Kashmir, and also animals in Qatar. So the applications for YOLO are mostly coming from the community. This is something like super interesting. So we don't actually know the extent to which people are using it. We only see these when someone kind of like announces on social media, comes to us and says, hey guys, like we created this like awesome app, or like we're doing this amazing thing with it. But I'm sure for every example we see here, there's 100 more that are buried that don't rise to the top. And of course, for medical use cases also. We've seen paper publications for things like breast cancer detection, mammography, ways that we can really start to automate medical processes that right now are out of reach for many due to medical costs, or in countries that socialize healthcare, perhaps larger backlogs. So it's really interesting the amount of use cases that are opening up by the availability of the technology, and of course, this nice marriage of hardware and software that we're seeing these days. So we wouldn't be able to do this without great advancements on the hardware side. So it's the two together that are really creating this synergy that we're seeing now. Okay, so I'm going to talk a little bit about a few details here. So what we see here on the left is an iterative loop, and this is how you want your AI model to live. A lot of people think of an AI training deployment as sort of like an open source arrow, like it just starts here, it ends there, and then you're done. But that's not the case. It should look like a circle. It should continue to iterate. The best example of this, I would say, is Tesla. They have a deployed autopilot system in their vehicles, in millions of vehicles, and the vehicles collect data. They collect edge cases and failure modes. They send those back for training and for redeployment. In this way, the system as a whole gets smarter and the vehicles improve over time. And this is absolutely elementary if you want to embed AI within a product. This is how your thinking should go for how you can create a system, not just to use an AI somewhere, but also to collect its failures, to analyze those and to augment those in either the data set or the model. So the second one is architectures. So we've worked a lot on improving architectures. And architecture advancements can somewhat make up for a data set that's insufficiently, I think, large or varied. But ideally, you want both. You want a data set that is adequately representing your deployment space. And of course, you do want the most advanced models, which is what we strive to produce here for everybody. And the last one here is tasks. So YOLOv8 supports many tasks now. So I mentioned a few before: classification, detection, and segmentation. We're also including key point detection for human pose estimation and other types of pose. It turns out animal pose is kind of a big deal too, and it has many use cases. So there's pose and there's also tracking. Tracking is now natively available in YOLOv8. We support different trackers. We've got bot sort and byte track, and we have an extensible framework to allow you to customize those or to add additional trackers. And we've also gotten a few requests. I think oriented boxes is a notable one, but we're always looking for ways to improve. So if you have a use case that we're not covering, definitely let us know. Okay, so with YOLOv8, we took to heart a lot of the criticism that we got in YOLOv5, which was that our documentation was terrible. And the users are absolutely right. The documentation was terrible. And the reason for this is because I was not a software engineer. So when I started creating YOLOv5, I had no idea what I was doing. It's more of an engineer, and I originally went to school for aerospace engineering. And so I did what I could in the documentation, but with my lack of experience, we see the result. And so this time, now that the team's bigger, now that we've had more feedback, we put a lot of effort into docs, and the docs are at docs.ultralytics.com. We're expanding them, but they explain almost everything: how to get started, the different tasks that YOLOv8 supports, different modes like train, predict, and advanced cases, how to customize things, how to use callbacks. So there's two ways to use YOLOv8. There's the Python and the CLI method. So these two share a common set of arguments. So it's sort of like two sides of a single coin. When you run these commands, the surface level code is slightly different. The way you interact with the model is different, but at its core, the exact same thing happens. So what we see here on this first line is an example of a predict command. This is simply YOLO predict. You say the model you want to use to predict and the source, and it's that easy. If this is a segmentation model, it'll know that, and it'll automatically apply segmentation inference. If it's a pose model, it'll also know that, and so on. And if you want to track, for example, then you would simply pass this a video instead of an image, and you would say YOLO track. So all of this is in the docs, but I think the recurring theme here is that we've tried to make this very, very simple. And of course, the way to install YOLOv8 is just pip install Ultralytics. That'll get you everything you need. It'll install Torch if you don't have it. So a bit of a warning is, if you have a special type of environment, you may want to install Torch ahead of time. If you have CUDA requirements or specific versions, you probably want to take a look at the PyTorch getting started website first. So the Python usage example is here. It's also very simple. We start with from Ultralytics import YOLO, and from YOLO you can create any model. You can load a PyTorch model like you see here on the second line. You can create a new model from a YAML file. This will be not trained. So this model won't be capable of predicting anything, but you can train this. I would not recommend training any model from scratch though. I would recommend starting from our pre-trained models like we see here on the second line. And you can not only load PyTorch models, you can load any of our exported formats the same way. So if you export to Onyx for, say, a speed up on CPU, you say YOLO, YOLOv8n.onyx. Or for TensorRT, you can do the same thing on GPU. So you can use the Ultralytics package not only to train, to export, but also to deploy and to run your exported models natively in their own formats. And this is supported for all tasks, which are detection, segmentation, classification, tracking, and soon pose. So we see a bit of a syntax here for training the model. Again, it's very simple. You point to a dataset YAML. And if you've used YOLOv5, then these dataset YAMLs are the same exact format. Everything's pretty easy. So let me zoom out here and go to the next slide. Oh, that's right. So another criticism, which was actually self-leveled within YOLOv5, was that there's too many places where settings could be changed. There's hyperparameter files, there's command line arguments, there's settings, some of which are hard-coded. And altogether, this meant that it was just too confusing to isolate a place where you could define all your settings. And with YOLOv8, we've simplified this greatly. There's only one place. Every setting is defined in a YAML called defaults.yaml. If you don't pass a new command line argument, it'll just take all the settings from there. So you can either change settings in the YAML file, or you can override those with manual commands like what we see here. So everything's really simple. And if you want to see a default value for a setting, you know where to go. Okay, so a little bit about architecture. Everybody seems to love the architecture. So YOLOv8 has some substantial differences from YOLOv5, and some of the key ones are here. So we adopted a split head. And this was, I think, first popularized by Mejvi with YOLOv8x, or just YOLOx. So Mejvi did a really good job there. We used a bit of a different architecture for a head than theirs, but the concept is the same. The concept is that you have different types of parameters that you're trying to estimate, which are things like regression for a box or key points and classification. And when you combine those features together, it makes it more difficult for the model to optimize for both. And so the split head, just like the name implies, splits the feature vector into two. And since each of these splits is only doing one task, like classification or regression, it's naturally better at that task than in YOLOv5, where the head is merged together and there's more multitasking going on. DFL loss is a big improvement also. So DFL, it estimates regression values at different scales and then combines these together in a matrix multiplication, a weighted combination of estimates, you could say. So whereas YOLOv5 would output only one box, YOLOv8 is outputting about 16 boxes and confidences for each, and then it's merging those together. And that's called DFL. And that allows us to, first of all, get rid of anchors. So this is a huge change also from YOLOv5. This is an anchor-free model that we have now with YOLOv8. This means that there's no more anchor evolution, nothing can go wrong on that step, and there's less parameters that you need to worry about. So it's a big simplification, and it's an accuracy improvement. You get better regression results. The last one is the C3 layer. So C3 layer is a name for a CSP bottleneck that was first invented by Wong-Kin Yu. And he had 4 different convolutions that were in this module, in addition to the bottlenecks. And so I simplified that down to 3 for YOLOv5. And now that's been simplified further in YOLOv8 to just 2. So in YOLOv8, we have C2 layers. And let's see here. Okay, so a few other architecture changes. We got rid of the focus layer early on YOLOv5, and now we've normalized the inputs to be similar to other models. So a lot of the architecture changes that we do aren't necessarily to improve accuracy. Some of them are to standardize models to make them more exportable to different formats. Since we have to export to so many formats, this means that we want our architectures to be composed of vanilla elements. We don't want exotic modules. Because even though that might work well in the laboratory, we're mostly interested in the real world. So we want our YOLOv8 models to be able to work on iPhones, Android devices, Raspberry Pis, pretty much like everywhere you can imagine. So this is a big caveat for everything we do at Ultralytics. It shouldn't be SOTA leading edge. That's not the most important thing. The most important thing is to get close to that while making sure that everybody can use these, that they're easy to train, that they don't use a lot of memory, that they're infinitely exportable. And again, these tasks. So I've covered these before, but now we got this cool graphic here that shows everything that we support now for YOLOv8. This last one is actually in progress now. We're training the very last key point models, and we're going to launch that soon as part of our next minor release, 8.1, which will probably be either this week or next week. So we're aiming to launch minor updates on a quarterly basis. So 8.2 should launch in about 3 months and so on. Okay, so with YOLOv8, we identify tasks, which we just saw on the last slide, and modes. So everything that you do has to be in a mode. And so we see the modes that are supported here. So you can train a model, you can validate it, you can run predictions with it, you can export it to another format like TensorRT. You can run tracking, which is essentially prediction interspersed with tracking steps. You can benchmark this, which will take a PyTorch model, export it to every format, and show you the speed of that format in the validation results on your hardware. Okay, and then we got Hub here. So I've been talking a lot, so I'll just cover this briefly. Hub is super awesome. If you haven't seen it yet, you should definitely check it out. There's a banner on the YOLOv8 repo, or if not, you can just go to hub.ultralytics.com. This is a no-code way to train YOLO models, and we're about to start supporting YOLOv8 for it. It's really friendly. We've tried to kind of model it off Apple software. We want it to sort of just work and to be intuitive. And it's designed for people that aren't ML experts. Like we want mobile developers to use YOLO, even if they don't know anything about ML. And that's what Hub is there to help people do. And the steps for Hub are super simple. It's just 3 steps here. So if you have a data set that you're using with YOLOv5 or YOLOv8, you can upload that to Hub. Cool thing is you can look at it. You can take a look at your data set. You can take a look at your labels, your splits. You can get analytics for it. It's really cool. It actually gives you much more insight than just using YOLOv5 or V8 by itself. The second step is you train a model. So you select your data set, you select your model. We support YOLOv5 and YOLOv8 soon. And the next step is just to select where you want it trained. We've got a Colab notebook that you can train on. Or if you have your own hardware, we show you how to do that too. And once it's trained, it uploads and syncs everything back to Hub, and everything is in the cloud, centralized. And if you want to, you can open up those models and you can share it with your friends. If not, it's private, and everything's free. And it comes with a really cool app, which is step 3. We've got a lead mobile developer who's been working on this. We have an Android app and an iOS app, and you can see your custom trained model right there in the app, like literally seconds after it's done training. Cool. Okay, I think I was supposed to do a demo, but it looks like we're out of time here. I might have talked too much. So I think, Dimitri, should we just jump straight into Q&A, or what do you think?
I think we can do the demo, a small demo maybe, and then go to the Q&A.
Okay, sure. I'll make the demo quick. All right, let's see here. So, okay, so I'm on Chrome browser right now. So let's do this. Let's say I go to Google and to find YOLOv8, where is it, right? Okay, so let's just say we go to Google, we type in YOLOv8, and the first link that's going to come up here is GitHub. So YOLOv8 lives at the Ultralytics/Ultralytics repo. And if you scroll down, you'll see some comparisons with other architectures. You'll see that the YOLOv8 models are smaller, faster, a little more accurate. You can see some actual benchmarks here. You can download the models. You can see some quick start code. But the easiest way to get started is right here. It's this little button, this opening Colab button. So ever since I started using Colab a few years ago, it's been tremendously useful. I don't actually have any GPUs locally. I work on a MacBook. So if I want to actually test some training, then Colab's a really simple way to do that. So you just click that badge and you come here and we see some code. And so the way to use these Colab cells, you just click this play button. And this first one is a setup cell. It's going to pip install Ultralytics. We really just need this one line. But the reason we have multiple lines is to show a little bit about the hardware and software that you're using, which is a summary that you see right here. So this is really useful. Since we have a Colab notebook that's on the free plan, we only get 2 CPUs and a tiny bit of RAM. But that's more than enough to run these YOLO models. Okay, so I've clicked this play button and it's running through here. It's downloading the Ultralytics pip package. You can see it's really small. It's about 500 kilobytes. And it's installing dependencies, most of which are already in Colab. So it's really quick. Okay, so we've installed YOLO. You can see that we're on version 8.0.61. And this minor patch I was telling you about will take this to 8.1 next week with the supporting pose. So once you've done that, you can run this next cell, which is a predict cell. This will run this code. I showed it in the other slide. It's just YOLO predict. You define the model. You say model equals YOLOv8n.pt. N is our nano model. It's the very smallest model. It's about 5 or 6 megabytes. It's only 3 million parameters. This is super, super small, but it's very capable. And that's it. So it's run inference. And you can see that it's taken 15 milliseconds here on this T4 CPU. Who got some pre-processing speed, which is less than a millisecond, and some post-processing, which is NMS time. So this NMS time, the first time you run a model, sometimes it'll be a little slower. So if it says 50 milliseconds, which just by my own experience, is simply a startup speed. So if we run this again, then it'll be much faster, about 1 or 2 milliseconds. That's something to remember. Like every time you're in inference, if a model seems slow, it's probably simply because it's like some just-in-time compilations. So we've run it again, and now we have an NMS time of 2.6. And our inference time went up a little bit. But again, we have really low statistics here. So to properly time these, you guys want to benchmark these with the benchmark command. So we see an example of the inference output right here. You can see it's detected 2 people, it's high. And validation is equally simple, just YOLO val, and you point to the data set that you'd like to val on. Once that's done, so since we have Cocoa trained models, you can validate those on Cocoa. If you don't have a Cocoa data set locally, it will download this automatically for you. Not just the Cocoa data set, but many other data sets like VOC, Argoverse, ImageNet, even if you're running classification. So training is, again, very simple. So we have just YOLO train. I think you guys are starting to get the hang of this. We define our model that we want to train. So we're just training the N size model, but if we wanted to say S for small, we just type S. Or the biggest model, X. We'll leave this at N. We define the data set. Here we have Cocoa 128, which is a small toy version of Cocoa. It's just got 128 images. We're going to train this for 3 epochs. And the default image size we use is 640 because this is about the max size that Cocoa images are. So we've run that command, and you can see that it's doing a lot of things here. It's creating the model, it's downloading the data set since it didn't exist here. This is the part where it downloads the data set. So in Ultralytics repositories, usually if something doesn't exist, it'll automatically download it from where it needs to. So it started everything. It's starting to train. It's done 1 epoch out of 3, and it's working on the second one. And you can see all this is happening very quickly, just in a few seconds. So it's going to finish training. It's going to run a final validation, and this entire thing is just taking less than a minute. So Cocoa 128, it's not a great data set to train on. It's just sort of a sanity check. So don't use the results you see there as an example. But this is sort of meant to show you the entire pipeline. Make sure you don't get any errors, and also so you can see like where models are downloaded and where they go. So if you go over here, you can see we've created a datasets directory, and we have Cocoa 128 here. And so if you want to train your own custom data, you can take a look inside here and see the format that your dataset should also be in. That's basically it. We've got export also. These are the different formats we support for export. If there's something missing here, which you'd like to see, just let us know. And a few examples for the different tasks. So this graphic is a lot of date since we've started adding more tasks like pose. So that's basically it. So in just a few minutes here, we've installed Ultralytics. We've run inference with one of our models on an image on the web. We've gotten results. We've validated the model. We've trained a model, and it's sitting right here. So, and all I've done is click a few buttons. So Colab makes all of this super simple. And of course, the next step is for you guys to try this yourselves, for you to get started, because this is an empirical science. And so that means that you have to get your hands dirty, you have to do trial and error, and that's the main way of moving forward and understanding things and then creating your own models and your own solutions. Okay, so that's it, Dimitri. That's the big walkthrough.
Good. Yeah, thanks for your presentation, for the demo. We have one questions on hand from Zoom. Argo, you can join us, turn on microphone and ask your question.
I see a question in the chat here. Oh, but this is a different question. Okay.
Yeah, it's different.
Yeah, hello. Glenn, first of all, thank you very much for your hard work. I really appreciate your long path and hard work path from particle physics. That's pretty awesome too. But I wanted to ask just one small question as I really love YOLO models and edge devices. I would like to know what is the way to go to run inference on something like Jetson. I of course used your exports to TensorRT, for example, which is really cool. But I wanted to know what would you recommend to use, like a backend, maybe Triton server or something like that. So what is the good way to go with it, with TensorRT model?
Yeah, that's a good question. So TensorRT is the fastest format that you're going to get on a CUDA device. So on CPU side, the fastest is going to be OpenVINO if you have an Intel CPU, or if not, then Onyx. But if you need more performance, then you need to export to TensorRT on a CUDA device. So even within TensorRT, though, there's different quantizations that you should be aware of. So the default export from YOLOv8 is just an FP32 export. So it's very simple to just add half to that. You can say YOLO export format equals tensor, format equals engine, and then space half equals true. And that'll export at FP16. And just from that, you'll be getting twice the speed. But then beyond that, there's also integer quantization, which we have limited support for, but which we need to pursue further, because that'll again provide further speed up for especially low power devices like Jetson Nanos. So Jetson's a great way to get started. There's also, I think recently we did a webinar with Seed Studio, and they talked about Jetson Nano Orin devices, which are using the new Ampere hardware, which are, I think, significantly more performant. They talked about something like a number they said was 20 tops compared to the original Jetson Nano at 0.5 tops. So 20 is a lot. And if that's true, that's actually more than like the latest generation iPhone also on a Jetson Nano device. So there's a wide range of edge devices. They also said that at the high end, the Orin devices will allow you to simulate smaller devices. So you could simulate the entire family and then select the minimum size that you need. So if you're going to deploy to 1,000 places, that might be really useful, because you don't want to spend more money or use more, I guess, energy or hardware budget than you need to there. So, but this is definitely like a big place that we've been focusing on. And I think it's a big differentiator compared to other companies, and also language models. Language models, I think, are always going to be in the cloud. They're just too big. But vision models, I think, really belong at the edge. And that's a big thing that we've tried to emphasize. And that's also not something you see too much at bigger companies like Google and Amazon. They're much happier for you to run your edge models right there in the cloud and charge you a little bit per image. But there's so many reasons that vision and edge like pair so well. So there's the privacy concerns, there's the latency, and there's the scalability. So if you're going to build like something big with like thousands of images or thousands of camera streams, that price is also going to scale in the cloud, but edge devices provide for a fixed cost. So,
Thanks a ton.
yeah.
Yeah. We also have the question about 3D box detection for point clouds from our chat. And not forget, you can use also Slando for ask questions. So please write the question there if you have. So yeah, about 3D box.
Yeah, 3D. Yeah, 3D is interesting. So when we're picking fruit from the tree, we start at the bottom of the tree and pick the low-hanging fruit. And this is detection. It's the sweet spot in vision AI. I think it's got about like an 80% market share. And then as you start to move out from that, then there's like less people doing more specialized tasks. But there are people doing 3D tasks, and we've gotten inquiries about that in the past. I think like a simple way to collect 3D data is through simulation. So we talk to people who are creating images using simulated data sets with tools like Unreal Engine, or even simulated data set providers like DataGen. And of course, once you have simulated data, you have the truth, and then you've got this 3D distance. You've got sort of like pseudo LiDAR. And that's pretty interesting. Right now, we don't have tools to support that. But I think another problem is the availability of like a commonly accepted reference data set. So it really helps like when you're considering a new task to have like a data set to start with. Even if you don't have a model or anything, you need a data set. And so once you have that data set, then you can really sit down and see the formats that you can export that to, what you need to do to modify your data loader, possibly new losses that you might need to introduce or replace. and also visualizations that you might want to change to help you introspect your results better. So it's not easy to adapt to a new task. There's a bunch of different places that need changes. But again, it all starts with the data set. So if there's, and again, I'm not a super expert on 3D data sets, but if there's a reference data set that's kind of like widely accepted in publications, I think the first step would probably be to make that available for auto download through one of our dataset YAMLs. And then from there, start creating a new data loader for it and then going on downstream. So the losses and then the validation and then finally the visualizations. So I think beyond pose, probably the next large task that we'd want to support would be OBB, which is oriented bounding boxes. It's a relatively small change, but it's significantly better for certain domains, like especially satellite imagery where rotation is unknown a priori. So for example, if you have a bunch of ships at 45-degree angles, YOLOv8 is going to do a bad job of that because the boxes are going to overlap so much. So OBB, I think, is our next step for additional tasks. Beyond that, maybe 3D. Who knows?
Okay, thank you.
Yeah. Okay.
You need more people.
Okay, well, I see a bunch of thanks here in the comments, so thank you guys. And of course, critical feedback is really important to us. We love people complaining, actually, because then it allows us to identify what we should focus on. So anything that you'd like to see better or pain points that you have with YOLO or just AI in general, let us know about that. And that's really invaluable for us to focus our future efforts on.
Yeah. Okay, I think we are all these questions for now. So thank you very much for your presentation, Glenn.
Yeah, thank you, Dimitri.
Yeah, thank you all that was with us. See you on the next webinars. Thank you and bye.
Great. Bye, guys.